Welcome all in the class of computer aided design of electrical machine. In the chapter 3 phase induction motor design, today's point of discussion is output equation of 3 phase induction motor. So what is the meaning of that output equation? Output equation is the mathematical expression which gives the relation between various physical and electrical parameters of the electrical machine. So for 3 phase induction motor or any number of phases induction motor machine, we can derive output equation. So we are considering M phase machine having one circuit, that is one parallel path per phase, and K variator machine we can define, that is Q is equal to, that is number of phases into output voltage per phase into current per phase. So current per phase into 10 raised to minus 3, because 10 raised to minus 3 converts volt ampere into kilovolt ampere. So we can take output voltage per phase as a EPH, current per phase is this IPH into 10 raised to minus 3. So Q will becomes M into EPH into IPH into 10 raised to minus 3. So for terminal voltage, we can use the EMF induced in the winding with the help of Faraday's laws of electromagnetic induction. That is that's value is nothing but the EMF equation of the winding. That is induced EMF per phase, that is EPH, we can calculate, that is 4.44 frequency flux, TPS that is number of turns, and Kw is nothing but a winding factor. That phi is nothing but a flux. So this equation will become Q is equal to M into 4.44 frequency into flux into number of turns, that is TPH in the winding, Kw that is winding factor, IPH is nothing but current per phase into 10 raised to minus 3. That value of EF can be calculated with the help of that equation P ns divided by 2, that is ns in the synchronous speed in RPS, that is rotation per second. So therefore we can write Q is equal to M into 4.44. We can replace that F with P ns by 2, that is P ns by 2 into phi into TPH Kw IPH into 10 raised to minus 3. So by calculating or by manipulating this equation, we can get this equation, that is 1.11 Kw P phi 2M TPH IPH ns into 10 raised to minus 3. So we are using here 2M by adjusting this 2e here. That's why the ratio is 1.11 kW. So Iz, that is current in each conductor, we can denote with Iz, that is current in each conductor. So we are considering one circuit, that's why Iz is equal to IPH for our case. So total number of armature conductors we can calculate, that is Z into number of phases into 2 turns per phase, that is equal to 2 mTPH, because one turn is nothing but a 2 conductor, that is Z is equal to number of phases into 2 turns per phase, that is 2 mTPH. So total electrical loading we can calculate, that is Iz into Z, that is ampere conductors, that will become 2 mTPH IPH. So the equation will become Q is equal to 1.11 kW P phi Iz into Z ns into 10 raised to minus 3, because we are replacing that 2 mTPH IPS by Iz by Z. So we can consider this P phi is nothing but a magnetic loading, Iz into Z is nothing but electrical loading, and into 10 raised to minus 3. So our equation will become Q is equal to 1.11 kW total magnetic loading into total electrical loading into synchronous speed into 10 raised to minus 3. But P5 we can calculate with the help of geometry, that is Pi, that is pi into dl into average of flux density, and Iz and Z, that is electrical loading, we can calculate with the help of the geometry Pi into d into AC, that is ampere conductors. So we can substitute this electrical and magnetic loading in the equation number 1. Then our equation of Q will become Q is equal to 1.11 kW Pi dl bav into Pi dac into ns into 10 raised to minus 3. That's ns is equal to synchronous speed in RPS. So by calculating this equation, our equation will be Q is equal to 11 bav AC kW 10 raised to minus 3 into d square L ns. So with the help of this pi into 1.11, the approximate value will become 1.11 into pi square, that is 11 bav AC kW 10 raised to minus 3 d square L ns, that is Q. The constant in the bracket is nothing but BAV AC kW. After the design of induction motor, we can consider this is a constant, because average flux density will be constant, AC also will remain constant, and winding factor after design will remain constant. That's why Q is equal to, we can denote this whole term or constant term with another constant, that is C naught. So C naught d square L ns. So Q will become C naught D square L NS, where C naught is nothing but output coefficient D square L into NH, where D is nothing but a diameter and length of the stator. Okay, C naught wave will be equal to 11 BAV AC kW into 10 to minus 3, which is known as output coefficient of the induction motor or machine. KVA input Q is equal to C naught D square LNS, and we can relate that KVA input with a output, that is KW, by dividing that KW by N cos of phi, where N is nothing but N or eta, we can say efficiency of the machine, and cos of phi is nothing but a power factor. So the rating of induction motor is sometimes given in horsepower also. So we can convert that horsepower into kW as per our requirement. And that output equation should be expressed in terms of horsepower. That's kVA input Q can be converted into horsepower by taking HP into 0.746 divided by eta into cos of phi, where eta is the efficiency and cos of phi is power factor. So horsepower, speed, power factor, and efficiency of a machine are specified. Therefore, in order to calculate the value of D square all, we can evaluate output coefficient by taking the value of C naught is equal to 11 and BAV, that's constant terms. Okay, the value of output coefficient depends upon the choice of electrical and magnetic loading. Okay, thank you.